Hey everybody, this is Larry. This is day 28 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think. Hope you had a great weekend. You know, sliding window maximum is today's problem. Okay, you're going to do sliding window, K numbers in the window, get the maximum. Okay. So I would say immediately I do recognize this problem as a max Q problem, or sometimes known as a mono Q or monotonic Q. I actually have a video that explains kind of the progression going to from how to solve what type of problem solves this is solved by mono Q or max Q. And just to be clear, max Q is not confused with max priority Q, which is a max heap. Max Q is monotonic Q or mono Q and something like that. I'll have a video linked below, or you can search for Leetcode Larry mono Q or something like that, and it should come up. I hope so. Otherwise, the algorithm is terrible. But yeah. So if you already know that, then this should be straightforward. And if you are not familiar with mono Q, that's okay. We'll go over it in this video. Maybe not as enough details to solve other problems. But to be able to solve this one, and I would definitely recommend that video as well, because I think people really like it in general. But yeah, so mono Q. And I would also say that, feel free to watch this on 2x or something like that, because I usually try to explain and solve this problem live. And in this, my disclaimer is that I vaguely remember the concept of mono Q, but it doesn't come up enough that I know how to type it or code it immediately. So we're going to discover this together. Let me know what you think. And yeah, so the idea behind mono Q is, and it's kind of funny because this didn't really used to be a name. It's just used to be a thing that people solve. And I don't know, I feel like nowadays everyone put fancy names on everything. But knowing the name of things doesn't mean you could solve things. So and that applies to me because I am a little bit rusty here. But anyway, back to the subject. So yeah, so the mono Q is basically trying to find an invariant that happens as you slide the windows from left to right. So let's say you have this example. Let me make it bigger just for a little second. So let's say you have this you have this thing, and now you have this sliding window. Let's say you have something like this, and then you just ask yourself, right, for each number, what are the possibles? Well, one is you could figure out, doing some maths for a given number, and it could be any number, what segments or what is the window in which this number is in, right? And then the second follow-up question is, in this segment and this number, what are, where can this number be the maximum number, right? And we'll go through it from, going from left to right. And for example, let's just do it one at a time. Let's have a pointer. Let's have a 1. Okay, 1 could be a max for right now, so that we just put in 1. And then now we kind of expand our segment to 2 numbers, because let's say k is equal to 3, because I think that's the example. Well, 3 comes into the picture, right? Yay. And then the question is, well, can one ever be how do you say this? Can 1 ever be the maximum number in any sliding window anymore? The answer is no, right? Because 3 will always be bigger than 1. The only place where 1 is a maximum sliding window is the prefix that goes before 3, which in this case doesn't exist because it's in the beginning of the array. So that means that we are able to get rid of 1 as a result. And then next we get the -1. Okay, -1, what does that mean? Well, can -1 be a max number? The answer is yes, right? I mean, I know that there's a 3 in front of it, but 3 goes away before the -1 does. So in theory, that is a possibility, right? And then now we slide. We remove the 1. We notice that it is not the max, so we don't care. Let's slide this as well. And then we add the -3. Same reason here, right? Draw the arrows a little bit more. -3 could be the max if the 3 gets removed or -1 gets removed, right? So we're going to put it into the queue, or whatever data structure, but let's just say it's in contention, right? And also one thing to notice, which you actually don't even notice, you don't even need to notice this, but it is an observation which gives the data structure, if you will, and the name, which is the mono queue or monotonic queue, right? The thing is that these conditions that we just talked about, the if statements that we talked about, means that everything here in a coincidental or maybe it's just, the property of how we approach this is that means that the numbers will always go from it'll be in a decreasing order for that reason, right? Because if a number is bigger than -3, then, well, we'll see what happens. Okay, now let's say we move on to the next. Well, 3 gets popped off because 3 is no longer in the running. Oops, just trying to draw ASCII art. And then we have 5, right? Well, that's the thing now, right? 5 is definitely the max starting at 5 for now. And then we look backwards. Can 5 be bigger than -3, right? Or maybe the other better question is, can -3 ever be bigger than 5 anymore? No, right? Because from now on, this segment and anything after that, either it pops off as we shift the sliding window to the right, or in which case 5 will be bigger anyway, or it pops off and then -3 is just going to be pop off, right? So that means that we can prematurely or preemptively remove -3. And the invariant that we ask ourselves is still true, which is that, okay, can -1 really be the max number anymore? The answer is no, not anymore, right? Because 5 will always be bigger than it, because that's how numbers work. So we put 5 here. And that's basically it. We'll do it again. We'll finish the array. So we'll move this here. 5, you have a 3 here. Wish there are more things. Let's just, for now, let's add in a number so I could have a better example. Let's say 4. Well, we only get rid of the 3 because 3 can no longer be a max, because it cannot be a max on the prefix because 5 is already bigger than it, and it can no longer be a max on the suffix because 4 is bigger than it. So we remove it, and then because 4 can still be a max, we keep 4 here. 5 is here as well. And then as we move, we pop off the 5, and in this case we add the 6, which we also pop off the 4, and then at the very end we get 7. So basically that is the way that I would trace the mono queue. Or the max queue. I call it max queue because you're trying to get the max number inside the queue. And then now we're going to move on to implementation. So now let's say we have a queue. As you go to collections.deck, we'll make this slightly smaller so it'll be easier for me to type. Hope that's still readable. Yeah. So now I wish I could move this to the right, because that's not really taking up so much room. Okay. And then now we have for index x in enumerate num, so that just gives us the index and the number. And then now, okay, now we add we do this thing, right? Which is that, okay, now first of all we add something to the queue on every number, because that's how, we always add a number in any case, right? Because either I guess we could do some invariants, depending on how you do it. But so there is an invariant here, which is that, okay, while length of queue is greater than 0, as we talked about. Let's say we go back to here, and we have -1, -3, and 5, and now we're just wanting to add the 5. Well, we can implement it in a couple of ways, but I'm going to implement it by just querying the -3 and then the -1 and then adding it, right? So that's basically what I'm doing here. And the last element of the queue, and do I have to keep track of the index? I don't think so. So yeah, I think we don't need the index, so we just get the last element of the queue. The last element of the queue is smaller than this element, then we pop right, everything just pop. Yeah, and at the very end we push x into the queue, and if index is greater than or equal to k, I think so. Let me double check this syntax. Or off. I'm just thinking about off by 1. So if k is equal to 3, at the index 2, we want to start counting it. So that's basically, so that means that we actually have index minus, if index is greater than or equal to k minus 1, then we check the biggest element on the queue. And as we said, because this queue is always going to be decreasing, I guess in this case it'll be, because this queue is always going to be in a decreasing order, the max element is always going to be in the front, right? So then, oh yeah, let's just say we have an answer, and then we return the front. And here the invariant is also that queue will have at least one element, because we literally just appended, right? So let's just set that up. And also we, not by we, the royal we, so I have to remember that we also need to, so this is the append function. This is part of the append function, because when you append, you remove stuff at the end, but we also need to handle the other case where you shift the window and you have to pop the front. So we just have to check if len sub q is greater than 0. Well, I guess that actually what I want to say is index of q is greater than or equal to k, because here we start popping off when we get to the third element, for example, right? Because when we get to the not the third element, but the index 3 element, then we have to start getting rid of index 0. So this is okay. So then we have to get rid of if q sub 0, and this is always going to be true that we have at least one element. You could prove that to yourself, though. If you want to be careful, you could check the length as well. If this is equal to the num sub index minus k, then we pop left. Okay, and that should be good enough to at least give a try. We'll go over it again in detail. This looks okay. Let me make this slightly smaller so I could make. Oh man, there's a lot of copy and pasting on this one, so maybe a little bit. Bear with me or fast forward this one a little bit. Well, these are very trivial examples, so I don't know that they test anything other than edge cases. But that looks okay. I'm just going to do like some bigger number thing. 4, say. Just to kind of see if it works, because they tell you the expected answer. If they don't, then I might have not done it, because I don't know if it would be right anyway. But this looks good, so let's submit it. And yeah. Yeah, so that looks okay. So what is the complexity of this? And again, that's what I do. When I solve these kind of problems, I talk about invariance a lot, and it is important for mono Q problems or max Q problems or whatever. It's very important to figure out what your invariant is when you go for each loop. And what I mean by invariant is just things that don't change as the loop occurs, right? The things that don't change is that here, the sliding window is k elements, and that Q have at least one element, and that Q contains, it's a monotonically decreasing Q or max Q, and that the first element is the max, for example, is another invariant, and there are a lot of invariants there for that reason. So let's talk complexity, right? What is the complexity? The reason why we like this is because it is O of n, right? Linear time, because we look at each number in the array at least, at most twice, once for pushing it into the queue, and then another time for popping it, right? So if you average it out, that is going to, even though there are while loops and funky stuff like that, it's going to be O of, because each element only gets looked at O of 1 times, it's going to be O of n because there are n elements. So that's linear time. And in terms of space, well, you can't really do better than O of n space because that we needed to return answer in this case. But in either case, the Q will be O of k, which is versus O of n as a result, right? So yeah, that's all I have for this problem. Again, I'll send a link below for the mono Q stuff. Let me know what you think. Hit the like button, hit the subscribe button. Have a good weekend, and I will see y'all later. Bye bye.